Right, good morning everyone. Welcome to the IvS seminar series. Today we have an internal speaker, Toon De Prins. He has been around already for a while, for a couple of years as a master student. So obviously he also did, maybe not that obviously, but he did his bachelor at KU Leuven as well. And he is one of those people who expressed some interest in doing PhD here at IvS, yeah, and then just rejected to accept money and said like, I'll get my own money, and he got FWO recently to work on jet formation and post-AGB stars. So Ton, I learned recently he has a lot of hobbies actually, and a lot of them are not that interesting in fact, but if you check the list on our seminar pages and you check the very last one, that's something that is really interesting. You might just consider borrowing that one as well. All right, Ton, the floor is yours. Tell us about jets in post-AGB stars, please.
Okay, so first of all, thanks for the warm introduction, Andrew, as always. And so yeah, welcome guys, welcome to the seminar. And first of all, it's nice to see this many bright faces around, but because that means you're all probably really excited to learn something new about post-AGB binaries. See? And or jets, you know. But all joking aside, this seminar is going to be on the subject of my master's thesis, which I defended last year, which is on the formation of jets in post-AGB binary systems. And specifically looking at the observations we have and trying to confront those with the models we have for the underlying disk model. So first of all, don't even need to use a laptop, I can just use a pointer. I'm going to run you through a small introduction first on post-AGB binaries in general. For the newer faces in the crowd, I think that's going to be really useful. For the older faces, you've seen this probably like 20 times already, but you know it's never too late to rehearse your post-AGB knowledge. But first, jumping right in, we're talking about jets, and that of course begs the question, what are jets? And in general, they're pretty loosely defined in astrophysics. They're just all very fast collimated bipolar outflows. But they occur in a very wide range of situations, and that ranges from planetary nebula, as you can see in the top left, or P&E, from active galactic nuclei, so from the supermassive black holes in the centers of galaxies, and to even young stars or young stellar objects, YSOs, where you have forming stars that again launch jets. And pretty much they're so universal because every time you have an accretion process and you have something of resembling a rotating accretion disk threaded by a magnetic field, you always get phenomena like this. You always get jets. And they span very different scales because, I mean, this can range from megaparsecs and this might just be a few light years in extent. But they're not the only systems in which we have seen jets. We've also seen them in post-AGB binaries, the systems I'm going to be talking about today. And they seem to be very low energy, non-relativistic, so in contrast to these big guys down here, which makes them similar to the jets launched by YSOs. So those are sort of going to be our main point of reference. Now, this cartoon here sort of shows you what a post-AGB binary typically looks like. And there's a lot going on, of course. They're complicated systems. So I'm going to be running you through the different components, first starting with the central binary, which consists of a large bloated post-AGB primary, that's an evolved star, surrounded by a much smaller main sequence companion. And this evolved primary star is on what we call the post-AGB track. So here on the left, you can see an HR diagram with some evolutionary tracks. And you see that you go from the main sequence all the way up to the red giant branch. Then eventually you reach the AGB track, or the asymptotic giant branch, where your star starts heavily expanding, becomes so cold, and the envelope becomes so loosely bound that you get dust-driven winds that then strip the outer envelope of the star. And that might look something like this in a binary system. This is from the Atomium project, led by our own institute's Léon Dessine. And after the envelope is stripped, what you have remaining is pretty much a naked carbon core that then becomes dynamically unstable and starts contracting and heating up. And that's pretty much this flat track here, and at the end it becomes a degenerate white dwarf and it just starts cooling off again. So this is your white dwarf track, this is your AGB track, and this flat phase in between is what we call the post-AGB. Very short phase, typically maybe a few thousand to maybe at the most for the lowest mass objects, 100,000 years. They're also very luminous, as you can see, typically from a few thousand to maybe 20,000, in some cases even a few factors higher in solar luminosities. The secondary star is a lot more boring. That's just the main sequence star. Well, there's a lot of stuff going on, but in terms of evolution, it's just the main sequence star. Now, the orbits that we measure for these binaries, and we do that using Hermes, actually, which is super nice, because that means that every time you guys go to La Palma and make some program ID 10 objects, put them into the list, I get a new spectrum. But from the orbital parameters, we see that the distances might be somewhere on the order of a few AU, sometimes a bit less. And what that means is that you expect interaction to have occurred on the AGB phase or the RGB phase when the primary sort of swelled up to giant sizes. And you might wonder, we're talking about post-AGB binaries. Why is the word RGB here in here, meaning the red giant branch? And that's actually because of the radial evolution of the star. Because you can see here for a 2-mass star, you sort of have a very small RGB tip, but the radius suddenly spikes when you get to the AGB. But for a 1-mass star, you can see that the RGB spike in radius is pretty much almost the same as for the AGB. So for these types of systems, we actually expect that binary interaction occurred earlier. And through Roche-Loeb overflow, so pretty much the companion pulling away the envelope of the primary evolved star, this might have already stripped the envelope on the RGB branch. So those are pretty much the analogs of these systems. So again, a flat track, but it would lie somewhere down here, for example. So we have low luminosity analogs of our systems that are actually post-RGB binaries, because the core was laid bare earlier. But for the rest of this talk, I'm just going to call all of them post-AGBs pretty much because they're very similar systems, and it's tough to discern between the two. So we know some type of binary interaction must have occurred simply because the radii of the primary become so big compared to the orbits that we measured today. So of course we can think, what kind of effect does that have on the orbital properties, right? Because if you get binary interaction, you expect the orbital properties to change. And what you can see here with all these systems are sort of measurements of the orbital properties for different kind of systems that have a white dwarf companion. And that's not only post-AGB binaries, they're in there, but for example, sub-dwarf B stars, like very weird stars. And in the background, you have this blue background that is results from population syntheses. And the deeper the color, the more probable you think that a binary will end up there at the end of its evolution. So you see here this sort of low eccentricity, circularized, low period branch, which is due to common envelope in the population synthesis. So you expect that your envelope just completely swallows the secondary. You get one single envelope enveloping both cores, the stars spiral in, and then the envelope is expelled, and you get, again, a post-AGB-like binary star. And then you expect a long period, kind of eccentric peak, which is due to the orbits being widened by the AGB wind. And what you notice is that all the measurements are right in between where you expect them to be. So there is something severely missing in our understanding of binary interaction physics. So while we're really not sure what is happening, maybe the common envelope is being avoided, it sure does seem to be the case, because you're missing binaries in this region here, we can see one of the results of the binary interaction. Because if we look around these systems, around this central binary, you see these big dusty disks of circumbinary material. And you might ask yourself, how do we discover these? How do we detect these disks? And that's actually pretty easy. You build yourself a few billion-dollar infrared space missions, throw them up into the sky, and what you get is a few photometric measurements at infrared wavelengths and maybe millimeter wavelengths. And what you notice then, if you look at the spectral energy distribution, where you have flux against wavelength, is that you have this first peak due to the stellar photosphere, pretty much. And then suddenly you have this strong excess in the infrared. And that's due to the dust actually lying around this system. And we discern that it's a disk and, for example, not a shell due to its location, because it's so close to the near infrared and because it's pretty extended. If you had a single dust shell that was ejected, you might expect maybe a peak here, a very narrow peak. And if we do that for all of our post-AGB sample in the galaxy, you see that around 30% of all post-AGBs show such a disk excess. And they're all binaries, pretty much. So this is how we detect the systems, and then we do radial velocity follow-up to measure the orbital properties, and we see that all of them are binary stars. So that means that this is a very mainstream evolutionary pathway, because if you assume maybe an initial binary fraction of 60% for low-mass stars, that means that around half of those stars actually manage to make such a big dusty disk surrounding the system. So these aren't niche objects. They're niche in the sense that you don't observe a lot of them because the evolutionary phase is so short, but they seem to be a very common result from low-mass binary evolution. And then, of course, we can ask ourselves the question, what is the link to orbital properties? And to be honest, I don't know, because nobody really knows. But it's, it's very probable that the disk itself has a strong influence on the orbital properties of these binaries, for example, in pumping up the eccentricity. But of course, SEDs only give you so much information, and they're pretty degenerate, so what we try to do is get some high angular resolution observations. So we try to use interferometry, and this is a very well-studied object that you can see with very many different instruments that have been targeting it, ranging from the VLTI, Pioneer, Gravity, Matisse, VLT Sphere for polarimetric observations, and in the end even ALMA more recently. But these are very far away. So these objects are typically at kiloparsec distances, and this 5 AU scale here, for example, that's about a few milliarc seconds. So we need interferometry to really be able to resolve the structure of these disks, at least the inner regions. What we've learned from those interferometric observations is actually that the structure of these disks is similar to protoplanetary disks, so the disks around young stars that tend to form planets, because we model them pretty much in the same way with passively irradiated disks, meaning that you just have a dust disk and its energetics are actually determined by the light it intercepts and reprocesses from the star. You also have some indication of structure formation in these systems, especially because about 10% of them are called transition disks, and that means that they have a typical excess in really near-infrared radiation, which seems to indicate that they have large holes in the middle. So these large holes probably have something to do with possibly the presence of planets within them, but I'm not going to dive into the details of that, just to save you some time. But these disks aren't really isolated from the central system because we have strong evidence that there is interactions going on in the form of reaccreting streams of material that fall from the circumbinary disk back onto the central system, probably both on the post-AGB primary and on the main sequence companion. And the evidence for this is twofold. The first thing that we do is we look at what's called refractory depletion. So we try to sort of look at the abundances of the primary star and order them by condensation temperature. And condensation temperature is a measure of how well your element tends to form dust, so dust-forming elements, let's say. And these here, all the way on at the end at high condensation temperature, easily form dust. You can see this correlation where the elements with high condensation temperature, and thus easily form dust, are systematically depleted. So that seems to indicate that there is somewhere a separation going on between dust and gas. And the idea is that dust is trapped inside the circumbinary disk, and then the gaseous phase is let through, now depleted of dust-forming elements, and that then falls onto the post-AGB's atmosphere and sort of dilutes it, starts mixing with the original material. And that gives you these strands. And in general, that also means that you get additional material falling onto your post-AGB primary star. So the idea there is that this also gives sort of not necessarily new fuel to the star, but it rejuvenates it and lengthens the post-AGB phase, possibly by a factor of 2 to 5 even. The second piece of evidence actually again comes from interferometric data. In this case of IRIS 08544, that's the same system that I showed here actually. And there we see not only the circumbinary disk, but if you look very well in this hole in the middle here, you can see this oval of emission that's actually unresolved, and it's centered on the position of the secondary star. So we think that there's actually an accretion disk surrounding the secondary star, formed due to reaccreting streams of material, and that then emits in near infrared. And that's cool because we don't see the main sequence star itself. It's not bright enough at all, so the post-AGB dominates all the energetics of the system. But if you have these accretion disks, like in this case, you can actually trace the position of the secondary and get some relative astrometry going, so you can start constraining the orbits, which is relatively nice. And this actually brings us to the topic of this work, right, of my master's thesis, which is the jets that were launched from these circumcompanion accretion disks, as we call them. And the way we do that is, again, with spectral monitoring. So like I said, we have Hermes, which is super nice, and we get to construct decade-long, even longer, time series of optical spectra with high resolution. And you get some nice stuff from that, like chemical analysis, so the chemical abundances of the post-AGB star, and the orbital properties of the binary. But what you can also see is actually signatures of the jets themselves. And for this, we actually represent our spectra in what's called a dynamic spectrum, in this case for the Balmer alpha line. And it might be a bit confusing, but let me run you through it. On the y-axis, you have the orbital phase. On the x-axis, wavelength, but in radial velocity space. And the color gives you the normalized flux. So every horizontal cut along this y-axis is actually a spectrum taken at a certain orbital phase. And then if you follow the flux, the color, it starts off as continuum, suddenly jumps to emission, photospheric absorption, an emission wing again, and then more continuum. As you can see here, for example, you have this sort of weak blue line. That's a small, weak absorption line. But it sort of follows this arc, which is actually the trajectory of the post-AGB along its orbit, but in radial velocity space. To break down how this actually represents the signature of the jet, I'm going to decompose this into two spectra, which is one here at the top at around orbital phase 0.1. And this is at the orbital phase where the post-AGB is not really behind the main sequence star. So if you look along the line of sight, they're separated compared to each other. And if you have a main sequence star that's launching jet material around it, the companion, the post-AGB itself is unobscured. And because that's the star that we see in the spectra, because this is an SB1, you sort of see a spectrum like this. So it's a background spectrum. If you then go to what we call superior conjunction, which is when the post-AGB is behind the main sequence star, you can see that this blue jet material sort of obscures parts of the post-AGB star. And suddenly what you see is this P Cygni-like profile with blue shifted absorption. So the idea is that the post-AGB's light passes the jet, is then scattered out of the line of sight, and because your jet is moving very fast, that results in very blue shifted absorption. And in the dynamic spectrum, you see that as this, well, blue shifted feature here, this absorption feature. So that actually holds a lot of information on jet density and kinematics, because you have this time series, so your post-AGBs, in a sense, scanning different parts of the jet as it moves in its orbit. And that means that we can do really detailed analysis of the jet structure. Whoops. So now I'm going to be running you through a few methods that we try to do in order to sort of reproduce these time series. First, starting off with the radiative transfer modeling. I'm not going to go into detail because that's not my area of expertise. But just really fast, we just pretty much evolve the position of the post-AGB and the main sequence. We attach some kind of jet structure onto the main sequence star, and then we let lines of sight from the post-AGB cross through the jet, and then we simulate how the light is scattered out of the line of sight and try to reproduce the dynamic spectra. But of course, that means we need to choose some kind of jet kinematic or density structure, right? And the thing is that there's multiple possibilities. Because these jets are so similar to the ones around young stars or launched by YSOs, we're going to be considering the same mechanisms that they currently are to explain their observations, and there's actually three of them. The first is the extended disk wind, and there you assume that inside your accretion disk, there's a large-scale magnetic field threading the entire thing. And it's this magnetic field that then sort of pushes up your material, launches it, and guides it along the field lines. The X-wind is a secondary scenario that's invoked for YSO jets, and there you assume that your accretion disk itself, this gray region here, is actually free of magnetic field. And it even acts sort of like a Faraday cage, so it has shielding currents, And what you have then is here the stellar magnetic field, so the stellar dipole, that sort of fails to penetrate the accretion disk. And that results in a sort of squeezed stellar field that then gets your field lines at a strong angle here, and then you assume that your material is sort of launched this way. And that happens in the theoretical models between the interaction region of the stellar magnetosphere and the accretion disk itself. The last scenario is the stellar wind or stellar jet, where you assume that the stellar dipole is strong enough to actually pull material from the accretion disk along its magnetospheric field lines onto the stellar poles. And this then shock heats the local atmosphere, giving you a sort of a Parker solar wind, but only locally at the poles, that is then guided by the open field lines of the star. And that also gives you a pretty collimated jet. Now, we're going to be choosing the first, the extended disk wind. We don't really know what the formation mechanism is in post-AGB binary jets, but this is a good place to try, because it seems to be favored by the observations, at least for YSO jets. This is a very complicated graph, so ignore 95% of it. But on the x-axis, you have the specific momentum. On the y-axis, the specific angular momentum of your jet material. And what you mostly need to focus on is the different regions, different colored regions in the plot, because you have this red region, which is expected by the extended disk wind scenario, and then this blue region that's expected by the stellar wind scenario. And these black symbols here, these are observations, and though you can see the error bars are pretty big, and they're sometimes tentative with only upper limits, it seems that all observations for YSO jets of their momenta seem to cluster in the region that's predicted by extended disk wind. But this is actually a plot from 2006, and these days we can do a lot better because we have some nice angular resolution. And what you can do is really look into the deep parts of the jet forming region, really look close to where the jet itself is formed. And these are two pretty cool results from a few papers, where on the left you have these red and orange dots, which are actually observed centers of water maser emission in a YSO jet. Overlaid on top of that is a simulation of a resistive extended disk wind. And then you can see that the qualitative behavior is pretty well reproduced, because you can see that the red dots, they kind of seem to arch, and that seems to indicate that they follow a helical pattern, while the orange dots seem to be more broadly outflowing, so it seems like they go under a shallow angle and then are suddenly collimated. And if you look at the field lines of these extended disk wind simulations, they follow the same behavior, where you have these very tightly wound inner field lines, and then these very big arcing field lines more to the side. On the right-hand side, you can see some carbon monoxide emission that's been resolved spatially and spectrally. And the color gives you the radial velocity. So you see a blue side of the jet that's actually moving towards us, and a red side that's moving away. And that's due to the rotation of the jet. So you can use this to really calculate specific angular momentum in your observations at different spatial locations. So that gives you very strong constraints on the mechanisms that could be responsible for such an outflow. And it seems that most of the observations seem to prefer extended disk winds. There's a few that are consistent with X winds, but for the most part, this seems to be the preferred mechanism. So we're gonna go with an extended disk wind. And how do you model that? Well, there's a few, let's say, solutions for this problem that describe the scaling of the properties, the scaling of the disk velocity field, the scaling of its density profile. And there's a few crucial parameters behind those kind of solutions that sort of determine how your jet behaves. The first one is magnetization. I'm just going to call it mu, which is the importance of the magnetic field in the disk, so it's a proxy for magnetic field strength. The ejection efficiency, xi, which is the amount of material deviated to the jet compared to your accretion stream, so it can go anywhere from between 0 and 100%. And then lastly, the disk aspect ratio, which gives you the thickness of the disk. So it's the ratio between pretty much the scale height compared to the radial coordinate. And you can see that not all combinations of these parameters actually give you solutions. It's a, let's say, discrete solution space where you have these islands, where you have separate dots of solutions that actually manage to launch a jet. All this white region in between fails. It tries to launch a wind maybe, but it could be that it falls onto the accretion disk again. So your actual solution space of disk launching objects with these parameters, jet launching objects, sorry, is discrete. In terms of the effect of these parameters, on the left, I'm showing you a very strongly magnetized but inefficient and thin disk solution, and on the right-hand side, one that's more weakly magnetized but more efficient and thicker. And I'm showing you the color plots for the density, the number density of hydrogen in these jets. If you compare the left to the right-hand side, it might be a bit of a subtle difference because it's in a log scale. But you can sort of see that your more efficient jet has higher densities. So that's a general idea. If you have more efficient jets, they manage to deviate more material to the jet stream, and that increases your jet densities. Looking at the velocity profile, this is the velocity sort of along the plane of the jet. And you also see that more weakly magnetized and efficient models tend to have lower velocities. So here you have high velocities, here it's a bit lower because you're missing those red ones. And you have a similar effect with rotational velocity, but compared to the thickness of the disk. So if you make your disk a lot thicker, the rotation speed tends to reduce a lot. So what I did is I took a few of these models, of these, let's say, fundamental solutions of the extended disk wind problem, took 5 of them, and then sort of put them into our radiative transfer code to do modeling and make some synthetic spectra and compare those to the observations. There's a few parameters that remain that you need to fit and that really give you a physical density and velocity structure for your jet. And because I'm annoying, I'm going to be counting counterclockwise, starting with the inclination, which is the angle between your jet axis and your line of sight towards the post-AGB star. Your accretion rate, which is simply the amount of material that you just ram into the disk on its sides, and that determines the density of the disk as well. The wind temperature, that's just for the radiative transfer, so we can just put a temperature in there and then see what it gives us, because that affects the excitation state of hydrogen and the depth of your absorption profile. The inner disk radius, which is just the inner radius of the accretion disk at the midplane. And what you then do is you draw a field line from that point that forms the inner boundary of your jet that you're considering. You have the same for the outer radius, which is here, and that gives us 5 parameters that we need to fit over. What I did is develop a very simple routine because I was slightly lazy, so I just made a grid fit over these parameters, assuming some reasonable values, and then applied that to 5 targets to see if this extended disk wind scenario, if it can even reproduce the spectra that we observe, and if it does, to see what kind of physical properties we actually expect for the underlying accretion disk system. So, going on to a few results. I'm not going to show all 5 targets, I'm just going to show a few interesting ones. Starting off with BD plus 46. Here you have your observations again in these dynamic spectra, and in the middle you have the best fit. I don't know if you noticed, but it's kind of wrong. It has a few properties that you don't see at all in the observations. And on this slide I wanted to focus on this one in specific. As you can see in your observations, this is just emission. You might have a slight bit of absorption here, but that's about it. But in the model, you suddenly have this redshifted absorption that occurs. And that's because the model jet is rotating too quickly. Because as the post-AGB passes behind the main sequence star, and your main sequence star's jet is rotating too quickly, the material is actually moving away from the observer. And that gives you a redshift in your absorption due to your jet that is way too strong here. And you can see if you turn it off, well, it's blue shifted again. So that's a problem. It seems that rotation is more suppressed in post-AGB binary jets compared to, let's say, the jets around YSOs. So that implies that you need higher epsilon to really slow down that rotation. You need thicker disks again, so that they start rotating more slowly. There's another problem with this fit. For those of you with a keen eye, you might have noticed that this is completely wrong as well. Because in the middle, you sort of have this emission shining through. And that's actually this left emission wing of your background spectrum that sort of shines through the model. So it's just indicating that your jet itself in the model doesn't have enough low velocity material to start absorbing here. And the issue or let's say the origin of that, we think, is the fact that we have a large cavity in the middle of our jets. So by construction, you can see that these extended disk wings, sort of, they span a winged X-like shape, but in the middle, it's totally vacuum. But there are reasons to actually expect more outflow components in these cavities. But the shape of that is difficult to constrain because it might be anything. So what I did is do a very simple test and assume that it's just a nice cylinder with a reasonable radius. It has a good velocity to really fill up this gap in absorption that we have here. And then I computed the extra mass loss rate that you would need inside this extra component. And it seemed to be, for this simple cylinder at least, under idealistic conditions, that it's only 0.1% of the remaining accretion that is still falling towards your star. So you have your accretion stream going in here, some part of it is deviated to the wind, and then the rest that falls onto the star here in the middle, only 0.1% of that is needed to actually fill in this gap that we have here. So it's reasonable to expect that if you have additional components inside this cavity, they might very well just use the remaining material that's there anyway with a low efficiency and manage to solve this problem. I didn't try any specific cases, but the cylinder model at least showed that it was possible. This is a much nicer example, IRIS 19135, my personal favorite, or at least it's at least second place, maybe the next one is even nicer, where we managed to sort of fit the observations pretty well. I mean, you can again see this lack of absorption due to this white stripe in the middle, but it's a lot more suppressed than in the previous case. But what you see, interestingly, is that you again have sort of this red-shifted feature due to jet rotation. Because if you remove rotation, it's completely gone again. So it seems that rotation suppression, it's there, also in this object, but it's less strong than in BD plus 46. So it seems that rotation of the jet is sometimes necessary to reproduce some of the small subtleties that you actually see in the observations over here. HP Lear, first or second place, I can't decide yet, so maybe you guys can. Here you have the observations, the best fit. It's pretty nice, doesn't match completely. There's some problems over here that you have in the observations that you don't see over here. And the absorption depth is sort of more shallow in the fit, but anyway, it's a nice model. But it's a strong exception, because if you look at its inner radius that it fits for the accretion disk, it's at 20 times the radius of the secondary star. So you have your star, and then 20 times the radius is only where your accretion disk would begin. That's very strange, because that means there's a gigantic cavity in the middle of this accretion disk, and it needs to be explained somehow. One of the mechanisms that's used to invoke these kinds of gaps in YSO jets and YSO accretion disks is actually magnetospheric funneling. So again, you assume that your stellar dipole is strong enough to really pull the material from the accretion stream onto the stellar poles. And that sort of creates a gap, as you can see in this simulation here. The problem is that the required field strength for that, for the star itself, would be on the order of 100 kilogauss. And that's completely unrealistic. You might think that there is a large accretion stream in our object and that this sort of falls onto the star, making it spin up and maybe rejuvenating its stellar dynamo a little, but there's no way that this can actually go up to 100 kilogauss. So it might be that we need to suppress things like the accretion rate, as you'll see later on in the conclusions as well, and then it might be reasonable to use magnetospheric funneling as a disk truncation mechanism. But at the moment, it doesn't seem realistic for this object, and we might need to consider some other methods to create this gap in the accretion disk. The last thing that I did was actually move away from the spectra, the dynamic time series that we have, and move on to something else, because we have one additional observational constraint for these accretion disks. And that's one disk temperature estimate that we have for IRIS 08544 from Michel Hillen's work in 2016, where he sort of spatially resolved, or at least managed to separate the light from the circumcompanion accretion disk from the rest of the system. And if you do that and you look at the spectral slope of that accretion disk's light and you try to fit it with a scaled blackbody to the H band in the infrared, he derived a temperature of around 4,000 plus minus 2,000 Kelvin. So then my idea was, okay, can I look at some of the fits I derived from my spectral time series modeling, and then see if I can discard any models that seem way too hot. So on the top left here, you see HP Lear. This is a disk model that sort of predicts a colder disk. It's only a few thousand Kelvin at most. And TWCAM here that predicts an extremely hot accretion disks in the inner region up to, 20,000 to maybe 30,000 Kelvin. So at first sight, you might think that this disk is way too hot to be considered a viable model compared to this observational estimate, if you assume IRIS-08 is representative for the whole sample. So what I tried to do is sort of recreate the experiment that they did in the observations by making some spectra for these disks. You can see the spectra here as the solid black line, and then fitted on top of that is this red line, which is a scaled blackbody. First of all, I know it's a bad fit, because you're trying to fit a multi-blackbody object with a single blackbody, right? So that's not going to work, because your actual object spectrum is sort of flattened at the top and much broader at the wings. But still, this is sort of a useful, rough, mean spectral temperature if you want to consider your full disk spectrum. And the values you get for HP Lear are, again, 2,500 Kelvin. That's fine, that's low, that's in line with the IRIS-08 observation. And for TWCAM, it's about 22,000 Kelvin. Even if you consider upper and lower limits, it's more than 10,000 Kelvin. So at first we thought again, okay, TWCAM's model is inconsistent with the observational estimate, and we might want to discard it. But the problem is here that we considered the full disk's spectrum. And if you look at the observational, the observational data, it's only taken in the H band, which is this narrow gray range that I've shown here. And if you do exactly the same experiment, just take the disk's spectral slope in the H band and try to fit that with a scaled blackbody, you get a different temperature estimate. So for HP Lear, we dropped from 2,500 to 2,300 Kelvin, no problem at all. But if you look at TWCAM, where earlier for the full spectrum you expected around 23,000 Kelvin, suddenly it's only 3,600 Kelvin if you look only at the H band. And that's weird, right? But that's a fundamental limit or a fundamental bias that you have if you're trying to fit the spectral slope of a multi-blackbody object with a single blackbody in a very narrow wavelength band. Because if you look at the spectrum here for TWCAM, your H band is all the way along the long wavelength wing of your full disk spectrum. And in these spectral regions, the only regions inside the physical disk that are contributing are the cold and geometrically large outer regions. And these typically only have a temperature of a few thousand Kelvin. So just the fact that you're looking at such a narrow spectral range completely biases your observational estimate to a few thousand Kelvin. So that means that we need more data, we need more spectral slopes. For example, if you had an extra band here, then you could definitely discern that this model would fit or not. But we are limited by the current wavelength coverage of the observations. So in conclusion, we have managed to successfully reproduce the general Balmer alpha features of at least two objects. That was HP Lear and IRIS 19135. But there's a few problems for the other stars, mainly because we have maybe the need for an extra component inside these check cavities to fill up this remaining absorption, and more suppression of the rotation. So we need even thicker disks. The interferometric H-band temperature that we had for one object actually seems extremely biased, so we need more interferometric measurements to make up for that. And the properties of the jet-emitting disk or the extended disk wind seem very different from the ones that we predict for young stellar objects. We seem to have a lot lower magnetization on the order of 10 to the minus 2 to 10 to the minus 3. And for comparison, for YSOs, that's 10 to the minus 1 to 1 typically. Very high efficiency of your jet forming mechanism, up to 20%, while it's around 0.1% for YSO jets. And very thick disks with aspect ratios larger than 0.1 compared to 0.01 for YSOs. And there's a reason for that. Because the thing that we've been neglecting or not have been talking a lot about in the structure of these accretion disks is actually the light from the post-AGB binary itself, because these are superluminous objects, right? at least on the order of 10,000 solar luminosities. So you can expect that if you have a post-AGB shining down on your accretion disk, adding a lot of heat in there, that you both heat up the outside of your disk, and then it puffs up, becomes thicker, and at the same time you also throw a lot of energy into the surface of the disk, and that sort of gives an extra thermal pulse or an extra thermal push to your jet material, which actually raises the efficiencies here. But we've neglected that for large parts in our current modeling. So as a result, we actually have very high accretion rates on the order of 10 to the minus 5 to 10 to the minus 3 solar masses per year, which are unrealistic, because that would imply a lifetime for the dusty disk around the system that's actually feeding these accretion disks on the order of 10 to 1,000 years. And that's too short, because we simply observe too many of these kinds of systems. So, finishing off with some future work. First, for the jets themselves, because that's not going to be a me, unfortunately, maybe for a part. First of all, we need to explore the full sample, and we currently have around 35 known jet launching systems. And this is just to show you some of the diversity in the different dynamic spectra that we see. Implement some of the missing physics in the model, starting off with the post-AGB irradiation, which will push your efficiencies even higher and probably reduce your accretion rates, solving the problem that we currently have with the estimated lifetimes for the circumbinary disk. Use some of the interferometric inclinations for the system, because that's one of our fitting parameters, right, that we fitted in our routine. But that's very degenerate with the rest of the properties. So if you manage to set the inclination, you free up a lot of computational resources and fix a lot of the degeneracies that you have just in your statistical problem itself. And of course, we need some other interferometry, maybe of the R band, so in the visual, to get a more reliable view on the temperature structure of these accretion disks, because we saw that using only the H band isn't sufficient. Now, future prospects for me, because I'm actually going to be doing something different. Same type of system, so post-AGB binaries, but for my FWO grant and in the context of the Inspiring Large program for the VLTI, I'm going to try and reconstruct some nice images of the circumbinary disks, look at their morphologies and see if we can't make any connection to the properties of the central binary and of the jets and the accretion disks, and sort of try to weave this into a consistent story about the evolution of these systems and the interactions that all the components have with each other. That's it for me. Thank you for your attention, and time for questions, I guess.
Thank you, Ton, for the very interesting talk. While people are thinking about their questions, I really liked your opening of the seminar, but there was one thing that you said, you referred to specifically, and that might be interesting to people in the room, some people at least. You said old faces. Can you please define old?
I'd point them out with my laser pointer, but I don't want to blind anybody.
Okay.
Guess it depends on the percentage of gray hairs, but I don't want to put limits just to be safe.
Questions? Yeah, we have two in front and one in the back.
Thanks, Tom, for this. Do you know anything specific or peculiar about the companions of these AGB stars? So I expect them to be very low mass or reasonably low mass May sequence, so maybe 0.5, even less solar masses. And they might actually be very, very magnetized, right? So it wouldn't be weird for them to have a strong dipole, jet launching wind.
Yeah, I agree with the fact that they probably have strong dipolar fields, right? Because especially if they've been spun up. But 100 kilogauss really is a lot, because for a heavily accreting YSO, you'd expect something of maybe on the order of 1 kilogauss. So this is 2 orders of magnitude higher. I'd believe 10 kilogauss, maybe, but 100 is really high. And in terms of the masses of these companions, we actually have like distribution estimates pretty much from the spectroscopic orbits and other constraints. And the companions are actually seem to be around 1 solar mass. So the idea is that, yeah, the heavier primary has, of course, of course, fully evolved, but it seems like the secondary companion's mass is really concentrated around one solar mass and higher. So that means the primaries were even more massive at the beginning, probably.
Or the secondary has accreted a bit.
Most likely during the AGB phase, maybe even now, because you have the accretion disk, of course, and there could be additional rush slope overflow due to the post-AGB star itself. But in general, we think the bulk of the accretion onto the secondary at this moment in time for their evolution
the
is from the
AGB is
disk.
shrinking, right?
Yeah.
Yeah.
So I want to hammer a bit on the 100 kilogauss and why that, because you're thinking in terms of accretion producing the magnetic field, but there could be the potential of the star intrinsically having that field. So for example, we recently found a strip star that has a 40 kilogauss field. So more or less it's within the factor of 2. I guess there's within a factor of 2 error on that number as well, theoretically. So I would ask, is there the possibility to falsify this observationally, just find Siemens splitting or polarization signatures?
It's very tough because you don't see the main sequence companion at all in the spectra. The only thing you can see really in direct light from the secondary is the accretion disk itself, and the secondary is masked out. So it's impossible to do Siemens splitting. The star you mentioned, is that the magnetar precursor that was discovered recently? Well, you should keep in mind that this 100 kilogauss is also dependent on the strength of the accretion stream that we derive, because you can imagine if you have higher accretion streams, it's sort of harder to pull your material away from the accretion stream itself. And these, of course, are a few orders too high, as you can see here on the bottom. So if we manage to suppress those down to maybe 10 to the minus 6, 10 to the minus 7, for example, by including the irradiation of the post-AGB star onto the accretion disk, this might drop down to maybe 10 kilogauss or something, and that I would believe.
Okay, thanks.
There's a question on the back here. Yeah.
Thank you. I was wondering if you had a suggestion for an instrument that could perform these airband measurements for your system.
Chara is the only one I know of.
Chara is not an instrument.
Chara. Do you remember the R-band instrument on Chara? I don't remember exactly. And you also have the Navy Precision Optical Interferometer, maybe. That might be useful as well. But I don't remember the names of the instruments. Sorry.
Thing is, I just cheated because during the first questions I was Googling this to see the name. But I think maybe Spica will be able to do it since it's working in the optical. Okay, thank you.
Hi, and wonderful talk. I was just wondering, so you had that plot of the refractory elements. Is it right if I get you to bring that up?
Yeah, it's way back.
Yeah, sorry, it was a while back.
There it is.
There we go. So I was just wondering, in the context of something you discussed very early, which is post-RGB versus post-AGB objects, are there certain signatures you might expect to see here that would allow you to distinguish between a post-AGB and RGB? Because in AGB, I mean, the main difference that I would think of is that you might find something like this. You might find a few quirky little bumps in this that would be signature of the nucleosynthesis.
Yeah. Those are your S process abundances, right?
Yeah, something like that. Like you might see this here, but I'm not sure what the signature would exactly look like, because you'd be looking for the absence of it in the RGBs, for example. But is this feasible, or is this dominated by disk physics?
It's just to get some context on this question. The reason that we currently can't discern between post-RGBs and post-AGBs is simply because our luminosity estimates are very poor, because Gaia data release 3 failed everybody in the binary community pretty much. But that would be the easiest, right? Get some nice distances, some good luminosity estimates, and if you see an object under 1,000 solar luminosities, it's probably a post-RGB compared to an AGB. But you're right, you do have, after the AGB, if there were some dredge-ups, it could be that they didn't occur because the evolution might be cut short by the binary interaction.
Yeah, could be.
But if you have S-process overabundances, like here, for example, all the way on the right, the zirconium ZR overabundance. That seems suggestive, right? That it must be a post-AGB. But that's again complicated by the fact that your profile here might be saturated by the reaccretion stream from the circumbinary disk. And that's just a linear slope in abundances. So if you have too much accretion from the circumbinary disk, even if you have overabundances in S process elements initially, that might be flattened out and sort of masked by the reaccretion stream from the circumbinary disk.
Okay, so you'd really, before you even started playing this game, you'd really need a good model of the system. Okay.
Yeah, which we don't.
Yeah, that's a hard problem. Thanks.
Are there any more questions? Yep.
Hi, thank you for the presentation. Could you go to slide, I think it's 29? You talked about the fact that rotation gives you this extra blue shift in the earlier part of the orbital phase.
Yeah.
But it looks like it also gives a blue shift at the later part of the orbital phase, which we do see in the observed, and is not present in the no rotation. So is there any other way to...
Do you mean this part?
Yes.
One thing that might be is actually, for example, let's consider this model here, which has no rotation, and you can see that it's sort of void of absorption in the middle, while here you have sort of a curve almost, where you have most of your absorption. That could be due to the fact that the jet is slightly tilted. If you tilt the jet slightly geometrically, your jet, the left edge that's sort of facing the direction of the orbit is kind of leading. Or it might be even retrograde, where if your binary star, your main sequence moves like this, that your jet is tilted like that. And that can sort of shift the morphology of your absorption signature so that it looks something more like this.
Okay, thank you.
Hi, thanks for the talk. So you keep comparing to YSOs, and my question is, so these are specifically the ones that you're looking at, massive, there's one massive in the binary and then a smaller one. YSOs also have a wide range of architectures. They can be binaries, one of them can have a disk, the other one not. They can be massive, they can be small. What kind of YSOs are you talking about? Are they specifically selected to be similar or not?
Most of them that have been selected for the studies of jets, at least, which is the main focus of this, most of the time they select single YSOs. And that can be anything, right? That can be RV Tauri, Herbix, but most of the time they select them to be single, just because if you have a binary, the binary can start pulling on the jet material as well, which I completely ignored here, of course, but that can complicate things a lot. So that's generally ignored in YSO jet studies.
So do you think that some of these inconsistencies could be caused by the fact that the comparison with the YSO is just not a representative system?
Yes, of course. Because they have different physics. Like, we know that these post-AGBs are so luminous, they must contribute to the energetics of the accretion disk on a large scale, which isn't always the case for YSOs. There have been some considerations, for example, for adding coronal disk heating in YSOs and stuff, but that didn't really work. But these have different properties in the sense that they have different magnetizations, different thicknesses. But the fact that we started with YSO jets is simply because that's the most similar type of jet that has been already discovered and studied extensively. So we had to start somewhere.
Right, okay. But I guess it's not surprising that they're very different.
No, not at all. It's actually surprising how well they match in some cases, because I didn't expect this one, or even this one to fit this well, which is a nice surprise. But you're right, there's discrepancies and those need to be studied in detail.
All right, thanks.
Are there any other questions? No, then I will have a couple myself done. So this spectra that you show here, you call them dynamical spectra, whatever. I mean, it's a time series folded on the orbital phase. What time scales on the orbital period, sorry? What time scales are we talking about here?
For these ones, I think I made a table somewhere, if I remember. 140 days to around 1,800. So that can be from a few hundred days to a decade in general, the orbits of these systems.
Right. So then the mass pronounced features span between whatever. So it's 1/5, right, of that. So 50 days to pretty much 400 days or something. And you try to model that from the perspective of the accretion disk, jet formation, stuff like that. But is there anything else going on in the system that could actually also contribute to the variability of your line profiles?
Definitely. The background, definitely. So you have different sources of variability, right? And that would be a really interesting thing to study for the systems for which we have a lot of orbits, actually, and some nice coverage to see how the structure changes as time evolves, really. But there's multiple sources. One of them is pulsations, as you can see here, because the Post-AGB itself pulsates radially, and that results in a very messy observed spectrum that you can try and correct for, but it's difficult to do so. An additional source is probably variability inside the jet structure itself, because these models that we use are steady state MHD models, but you expect a lot of turbulence and a lot of clumping and maybe other effects inside the jet stream itself and inside the accretion disk. But unfortunately, we are not at a level where we can model that reliably at the moment.
Thank you. Any more questions? Yeah.
Hey, Toon. Thanks for the talk. My question is actually, do you have any constraints on the collimation of the jet through your spectral features, like the P-Cygni profile, for example? And could that add constraints to the inner and outer disk boundaries?
Collimation would be really useful to understand. But the problem is that we're looking through, and you'll probably see that at this point in this plot. The collimation far away, well, the collimation itself, let's say, happens far away in vertical distance from the central system. And what you're probing here with your lines of sight is pretty much the inner AUs of the system. And there you still have a lot of bending of your field lines before they really become straight and form a nice cone of which you can measure the opening angle. And for that, you'd need some larger scale images of these jets. And I don't think we have any of those at the moment. But then we might be able to constrain the opening angle.
Can I just go for a last one? This is related to the question from the back with the depletion of elements, right? And the distinction between post-AGB and RGB. What does this mean for carbon? Because you also expect carbon enrichment for post-AGBs, I mean, from the, after the AGB evolution. And is there any distinction at all?
I don't think we really understand that yet. It's a very complicated problem, of course, to trace the nucleosynthesis through all these interactions that are happening, even on the AGB and these binary interactions that we don't understand at all. But for example, what we see in the disks themselves, in the dust, is that that's a recent paper by a Spanish group, where they see that 13CO, so CO13, the isotope, seems to be underabundant compared to 12CO. CO12. And that seems to indicate that probably the evolution of the AGB was cut short somewhere before your dredge-ups are really efficient. So it depends on where the evolution is cut off along the binary interaction. I don't know how that is for the full sample, though. I don't have a good view on that at the moment.
Thank you.
All right, we're at the hour, so thank you everyone for coming. Let's thank Toon again, and I'll see you next week.